We shall discuss about the chapter mean value theorems. It is application of derivative. What is the first theorem? It is Rolle's theorem. If a real valued function fx defined on closed interval ab is continuous in closed interval ab, derivable on open interval ab, and if the functional values at the extreme point, that is f of a is equal to f of b, are equal, then there exists at least one real number c between a and b, that is a less than c less than b, such that f dot c is equal to f dash c is equal to 0. That is the first order derivative of that function at that particular point c is equal to 0. I am again telling, what is this real valued function? What do you mean by real valued function? Real valued function means that is for all values of x, that is for every point in the domain, the functional values are real. The values of f of x are all real for all values of x. Now closed interval and open interval. What is closed interval? Now including the endpoints, that is including the point a and b. Okay, and what is open interval? That means just excluding the endpoint, that is from A to B, not including the points A and B. Okay, so a real, again I am telling the theorem, that is Rolle's theorem. If a real valued function fx defined on closed interval ab is continuous, three conditions the function will satisfy to follow Rolle's theorem. What are the three conditions? The first condition, it will be continuous on closed interval ab. Second condition, it will be derivable on open interval ab. And the third condition, that is the functional values at that extreme points are equal. That means f of a is equal to f of b. If the function follows these three conditions, then only we can say that there exists a point c in open interval ab, that is a less than c less than b, such that f dash c is equal to 0. That means the first order derivative at that point is equal to 0. Okay. Mean value theorem, that is Lagrange theorem. This is also known as the first mean value theorem of differential calculus. What is Lagrange theorem? The same thing. If a real valued function f of x defined on closed interval ab is continuous on closed interval ab and derivable on open interval ab, then there exists at least one real value c in open interval ab, that is a less than c less than b, such that f dash c, that is the first order derivative at that particular point c, is equal to f of b minus f of a by b minus a. You see what is the difference between Rolle's theorem and Lagrange theorem? In Rolle's theorem there is a third condition, that is the value of the function at the extreme points are equal, that is f of a is equal to f of b. But in case of Lagrange theorem, the third condition is not there. Okay, the function, the real valued function fx follows only the two conditions, it is continuous on closed interval ab and it is derivable on open interval ab. Then there exists at least one real number c in between a and b, that is in open interval ab, such that the first order derivative at the point c, that is f dash c is equal to f of b minus f of a by b minus a. Let us see the geometrical significance or geometrical interpretation of this theorem, that is Rolle's theorem and Lagrange theorem. What is Rolle's theorem? Now if a function it is defined in the closed interval ab, which is continuous in the closed interval ab, you see the graph is continuous for this function f of x, derivable, and if at the end points, that means at a and at b the functional values f of a and f of b are equal, then there exists at least one point c in this open interval AB, in between AB, such that f dot c is equal to 0. That is first order derivative of that function at that particular point c is equal to 0. First order derivative is equal to 0 means at that particular point the tangent is parallel to x axis. Slope of the tangent is equal to 0. Okay, first order derivative 0 means slope of the tangent is equal to 0. That is the tangent is parallel to x axis. Here you can see the significance of that word at least one point C in the open interval AB. Why at least one point? There may more point exist. Let us see the second graph. You see this is the graph. Here this is the point A and this is the point B. So the functional values are same equal, that the end point, third point is satisfied, f of A is equal to f of B, and from the diagram, from the curve, we can see this function f of x, it is continuous as well as derivable. So you can see, you see C1, C2, C3 and C4, 4 points are there on this graph where the tangents are parallel to x axis. That means in all these points the tangents are parallel to x axis. That means the first order derivative at the point C1, C2, C3 and C4 are 0. Okay. Again I am telling, at C1 C2, C3 and C4 in all points the tangents are parallel to x axis. That means f dot c is equal to 0. Okay. Now the geometrical significance or geometrical interpretation of Lagrange theorem. What is that? You see, in this curve, that is f of x, the function is continuous in closed interval AB and derivable in the open interval AB. From the graph we can see. Okay, and you see in the end points the functional values are not same. F of A not is equal to f of B. So in this case we will get at least one point C in between A and B in closed interval AB, such that the first order derivative at that particular point, that is f dash c, is equal to f of b minus f of a by b minus a. That means the tangent at that point is parallel to the chord joining the points a comma f of a and b comma f of b. Here in this graph you see, that is the significance of the word at least. That means there exist more points than one point. There exist more points where the tangents are parallel to the chord joining a comma f of a, b comma f of b. You see, at the point C1 the tangent is parallel to this chord, as well as at the point C2 the tangent is parallel to this. Let us solve some problems from this chapter. The first problem, it is given, discuss the applicability of Rolle's theorem for f of x is equal to 3 plus x minus 2 whole to the power 2 by 3, and the interval it is given closed interval 1 comma 3. Now we can see for all, this is the symbol of for all. For all x belongs to closed interval 1 comma 3, the value of fx are real numbers. So that means for all values of x in closed interval 1 comma 3, fx has a real value. So fx is continuous in the closed interval 1 comma 3. Next we have to check the derivability of this function. What is given? Fx is equal to 3 plus x minus 2 whole to the power 2 by 3. So f dash x, differentiating the function with respect to x, we will get this. Now you see, if you put x equal to 2 here, that means 2, why 2? As 2 lies in the open interval 1 comma 3, 2 is a point between 1 comma 3. So if you put 2 here, ultimately it will be 1 by 0, that is undefined. So f dash x does not exist. That means fx fails to be derivable on open interval 1 comma 3. That is, fx is not derivable on open interval 1 comma 3. And f of 1 is equal to 4, f of 3 also equal to 4. That means all these three conditions, that is continuity, differentiability and the functional values at the endpoints, we have to check. Okay. If all these three conditions are satisfied, then only we can say that Rolle's theorem is applicable, otherwise it is not applicable. Here you see fx fails to be a derivable function on open interval 1 comma 3, that's why Rolle's theorem is not applicable on fx, that is 3 plus x minus 2 whole to the power 2 by 3 on closed interval 1 comma 3. Let us see another example on Rolle's theorem, that is verify Rolle's theorem for the function f of x is equal to x square minus 4x plus 3 on closed interval 1 comma 3. So this given function, it is a polynomial function. If it is a polynomial function given, just you write that every polynomial function, it is continuous for all real values of x. That means fx is continuous for all x belongs to closed interval 1 comma 3. Now we have to check derivability. Okay, fx is equal to x square minus 4x plus 3. So f dash x is equal to 2x minus 4. It is also exist for all x belongs to open interval 1 comma 3. So fx is derivable for all x belongs to open interval 1 comma 3. Now f of 1 is equal to 0, f of 3 is equal to also 0. That is the functional values at the extreme points are equal. So all these three conditions are verified. So Rolle's theorem is applicable. That means there exists at least one point C where f dash c is equal to 0 and c lies in the open interval 1 comma 3. Let us see whether it is true or not. So f dash c is equal to 0, that means what is f dash x? 2x minus 4. So f dash c will be putting the c in place of x, we will get 2c minus 4 is equal to 0. That means c is equal to 2. Where this 2 lies? 2 lies in the open interval 1 comma 3. That means 2 lies in between 1 comma 3. So Rolle's theorem is verified. That means we got a value 2 which is in the open interval 1 comma 3 where this first order derivative is equal to 0. Now we shall see one sum from Lagrange mean value theorem. That is verify Lagrange theorem for fx is equal to root over of 25 minus x square on closed interval minus 3 comma 4. So at first we have to prove it is continuous. So if x belongs to closed interval minus 3 comma 4, so x square is greater than equal to 0 and less equal to 16. From that, by calculation we will get this root over of 25 minus x square, it is greater than equal to 3 less equal to 5. That means fx is continuous for all the values of x in closed interval minus 3 comma 4. Now the differentiation of this one that is root over of 25 minus x square, what is the differentiation? This one. Now this derivative, this value does not exist if this denominator becomes equal to 0. But you see, for all real values of x belongs to open interval minus 3 comma 4, this root over of 25 minus x square or this 25 minus x square, it is greater than 0. Okay, this 25 minus x square, it is greater than 0. That means the square root of this 25 minus x square, it exists. Okay, so fx is derivable on this open interval minus 3 comma 4. If this term under this square root, it is 0 or negative, then it fails to be a real number. Then only we can say that it is not derivable. But here you can see this 25 minus x square, the term under square root, it is greater than 0. So f dash x, it has the real value. That means fx is derivable on open interval minus 3 comma 4. So both these two conditions are satisfied. That means Lagrange theorem is applicable. As Lagrange theorem is applicable, that means there exists at least one point C in this open interval 3 comma 4 where f dash c is equal to
f of b minus f of a by b minus a. b is here 4 and a is minus 3. Okay. Now f dash c, what is f dash c? Putting x is equal to c here, we will get f dash c, that is minus c by root over of 25 minus 6 square is equal to this. Okay. Then by calculation we will get c is equal to plus minus 1 by root 2. That means two values are of c exist here, and both these plus 1 by root over of 2 and minus 1 by root 2 both lies in this open interval minus 3, 4. That means Lagrange theorem is verified.